Now let us look at the forces acting on fluids. We can have three kinds of forces: point forces, surface forces, body forces. We know we can't apply any point forces to fluids, unlike the solids. Therefore, we are not worrying about point forces in fluids. Can we apply surface forces? Before we look at the application, let us look at the types of surface forces. Again, we can differentiate surface forces into three categories. The first one is compression or squeezing. Second is tension or pulling. Third is shear or tearing or twisting. Compression or compressive force. In fluid mechanics, we call this is the pressure force, and the resulting stress is pressure. We know solids are less compressible, but gases are highly compressible. What can we say about fluids? They are compressible, unlike solids and gases, but in between them. Now we will move to the tension or tensile forces. If we apply tensile forces to liquids, we can vaporize the liquids. Therefore, at this level, we are not focusing to tension of liquids. How about the shear forces on liquids? If we look at solids, they can deform to a certain limit due to shear. When we further increase the shear force, the solid object can be permanently distorted. However, situation is different in liquids. We can indefinitely distort the fluid under the shear force. This brings the definition of fluids. A substance which deforms continuously under the action of a shear force is called a fluid. You don't really have to remember this or cram this definition, but just read it and understand the definition. Now, let us talk a bit on the distortion due to shear. If we consider the rate of distortion, it has to be proportional to the applied shear force. Let us consider ABCD cube and assume it has distorted under the shear. Now, distorted angle is theta to the vertical. Therefore, the distorted rate is theta in a time of delta t. So, theta divided by delta t. Now, we all know that is the angular velocity omega. Now, let us try to obtain this theta from geometry. We know the angle can be defined as the arc divided by the radius. Now, let us look at the arc. If we look at the velocity diagram, we can say that the displacement of side D with respect to C is delta U into delta T. Now this is from the relative velocity concepts. Therefore, we can define theta to be arc divided by radius, that is delta U delta T over delta Y. Now let us substitute that to omega which is equal to theta divided by delta T, that is going to be delta U over delta Y. Now we know shear force is proportional to shear stress, which is proportional to omega angular velocity, which is proportional to delta U over delta Y, that is the rate of rotation. Now therefore the shear stress tau is proportional to delta U over delta Y. Now how can we remove this proportional symbol? You may recall from your high school physics and mathematics, you substitute a constant to remove the proportional symbol, but it is not a constant, it is a function. Now if we consider that function to be pi, so tau is equal to pi du over dy. Now the experiments show various types of functions. If we look at the plot against shear stress to the shear rate, we can have different types of functions, and they are called plastic, Newtonian fluids, ideal fluids, and so on. Now, in the context of this module, we'll be only looking at the Newtonian fluids, that is to go with y equals mx. Y stands for tau, m stands for mu, x stands for du over dy. Therefore, our equation for shear stress is tau is equal to mu du over dy, which is called the Newtonian law of viscosity, where mu is the dynamic viscosity and a property of fluids and temperature. Now, what is a Newtonian fluid? Please search and understand what is a Newtonian